Preparing for a Databricks Engineer interview, you've reached Candy Mentor, and this video is for you. We'll walk through 21 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. What makes Apache Spark faster than traditional MapReduce? And where can it still bottleneck? Spark improves on MapReduce by keeping intermediate data in memory and building a DAG instead of forcing every step through disk. I would explain transformations, actions, lazy evaluation, and stage scheduling. But Spark is not automatically fast. Wide shuffles, skewed keys, poor partitioning, small files, and excessive serialization can dominate runtime. In production, I tune partitions, cache selectively, inspect the Spark UI, and reduce unnecessary data movement. While answering, focus on Spark's execution model, in-memory computation, DAG scheduling, lazy evaluation, shuffle costs, and practical bottlenecks like skew, serialization, small files, and inefficient transformations. Question 2. Explain the roles of the driver, executors, and cluster manager in a Spark application. A Spark application starts with the driver, which builds the logical plan, coordinates scheduling, and tracks metadata. Executors run on worker nodes and execute tasks against partitions. The cluster manager allocates resources, whether it is Kubernetes, Yarn, or Databricks job clusters. I describe jobs, stages, and tasks, then connect failures to retries and lineage. The key interview point is that performance depends on partition sizing, executor resources, and shuffle boundaries. Make sure to cover driver, executors, cluster manager, jobs, stages, tasks, partitions, resource allocation, lineage-based retries, and how these concepts show up in Spark UI debugging. Question 3. Given a very large event log dataset, how would you find the top K most frequent events efficiently? I would solve it locally with a hash map plus a min heap of size K, giving O of n log K. For distributed data, I would aggregate counts per partition first, then combine partial counts and apply top K globally. In Spark, that means reduce by key or group by with aggregation, not collecting raw rows. I would also mention skew handling if one event dominates, because hot keys can overload a reducer. In your answer, talk about local algorithm complexity, distributed aggregation, avoiding collect, partition-level pre-aggregation, handling skewed keys, and how the approach changes from single machine code to Spark. Question 4. How does Delta Lake provide ACID transactions on top of cloud object storage? Delta Lake adds a transaction log on top of cloud object storage. Each commit records file additions, removals, schema changes, and metadata, which enables snapshot isolation and time travel. Readers see a consistent table version, while writers use optimistic concurrency control. That is crucial because object stores do not provide database-style transactions. I would also mention compaction, vacuum, and schema enforcement as practical features that make lakehouse tables reliable. Be sure to mention the Delta transaction log, optimistic concurrency, snapshot isolation, ACID semantics on object storage, time travel, schema enforcement, compaction, vacuum, and why reliability matters. Question 5. A Spark job in Databricks is suddenly running much slower. How would you debug and optimize it? I start with the Spark UI, not guesses. I check stage timelines, shuffle read and write, task skew, spill, GC time, and input size. Then I map symptoms to fixes, repartition for parallelism, broadcast small dimensions, avoid UDFs when built-ins work, cache only reused data, and compact small files. If skew appears, I use salting or adaptive query execution. The best answer shows a diagnostic loop, not a random tuning checklist. While answering, emphasize a systematic debugging workflow using Spark UI metrics, physical plans, shuffles, spills, skew, partition counts, caching decisions, broadcast joins, AQE, and file layout. Question 6. What is the difference between narrow and wide transformations in Spark? Narrow transformations like map and filter use data from a single parent partition so Spark can pipeline them efficiently. Wide transformations like group by key, join, and distinct require data to move across the cluster through a shuffle. Shuffles create stage boundaries and often dominate cost. In interviews, I connect this to design choices. Prefer reduce by key over group by key, pre-filter data, partition by join keys, and avoid unnecessary global operations. Make sure to cover dependency types, shuffle boundaries, stage creation, examples of each transformation, why wide operations cost more, and coding choices that reduce data movement. Question 7. How would you build an exactly once streaming pipeline using Databricks structured streaming and Delta Lake? Exactly once is achieved by combining deterministic processing with transactional syncs. In Databricks structured streaming, I would use checkpointing for offsets and state, Delta Lake as the sink, and idempotent writes such as merge keys or for each batch with transaction control. I would discuss watermarking for late data and state cleanup. The honest nuance is that external systems may only support at least once, so the pipeline must make retries safe. In your answer, discuss structured streaming checkpoints, offset tracking, state stores, delta transactional syncs, idempotent writes, for each batch, watermarking, late events, retries, and limits with external systems. Question 8. What is data skew in Spark? How do you detect it? And how do you fix it? Data skew means some partitions receive much more work than others, usually because a few keys are extremely frequent. It shows up as straggler tasks in the Spark UI, while other tasks finish quickly. I would fix it by salting hotkeys, splitting large partitions, broadcasting small tables, using AQE skew join handling, or redesigning the aggregation. The goal is balanced parallelism. Simply adding more executors often hides the real issue. Be sure to mention how skew appears in Spark UI, common causes like hotkeys, effects on straggler tasks, and fixes including salting, broadcast joins, repartitioning, and AQE. Question 9. How would you design a scalable lakehouse pipeline for analytics and machine learning features? I would land raw events in bronze, clean and standardize them in silver, then publish curated feature tables in gold. Delta Lake gives schema enforcement, versioning, and incremental processing. For reliability, I would make jobs idempotent, track data quality expectations, and separate orchestration from transformation logic. For ML use cases, I would care about point-in-time correctness to avoid leakage. The design should optimize both batch backfills and fresh incremental updates. While answering, focus on bronze, silver, gold layers, incremental processing, data quality, idempotency, lineage, point-in-time correctness, backfills, orchestration, and serving both analytics and ML use cases. Question 10. How do partitioning, bucketing, Z-ordering, and clustering affect query performance in Databricks? Partitioning physically separates data by column values, like date or region, so queries can skip entire directories. It works best for low or medium cardinality predicates. Bucketing or clustering organizes data within files to improve joins and data skipping, without creating too many folders. In Delta, I would also mention Z-ordering or liquid clustering. The trade-off is write complexity and metadata overhead, so I partition only on columns that consistently filter queries. Make sure to cover partition pruning, cardinality trade-offs, bucketing or clustering, Z-ordering, liquid clustering, file skipping, metadata overhead, write amplification, and choosing columns based on query patterns. Question 11. How would you handle schema evolution safely in a production Delta Lake table? Schema evolution should be deliberate, not accidental. I would enforce schemas at ingestion, allow additive changes only through controlled configuration, and validate incompatible changes before writing. Delta supports schema enforcement and merge schema, but I would use them carefully because silent type changes can break downstream consumers. I would also version contracts, run data quality checks, and communicate deprecations. In lakehouse systems, schema governance is as important as compute tuning. In your answer, talk about schema enforcement, additive versus breaking changes, merge schema risks, type compatibility, downstream contracts, data quality tests, governance, and versioned communication with consumers. Question 12. How does Spark choose a join strategy? And when would you use a broadcast join? Spark chooses join strategies based on table sizes, statistics, hints, and configuration. A broadcast hash join sends a small table to every executor and avoids shuffle on that side. Sort merge joins handle large tables but require shuffling and sorting. Shuffle hash joins can work when partitions fit memory. I would explain how I collect stats, use broadcast hints carefully, filter early, and inspect the physical plan with explain before tuning. Be sure to mention broadcast hash joins, sort merge joins, shuffle hash joins, table statistics, join hints, physical plans, predicate pushdown, filtering early, and memory trade-offs. Question 13. How would you design reliable production job orchestration on Databricks? For production jobs, I separate task dependencies, cluster configuration, parameters, and environment management. Databricks workflows can orchestrate notebooks, Python wheels, SQL tasks, and DLT pipelines with retries and alerts. I would use job clusters for isolation, version code in Git, pass secrets through secret scopes, and log metrics. A strong design includes backfill strategy, idempotent outputs, failure notifications, runbooks, and clear ownership for on-call debugging. While answering, cover Databricks workflows, job clusters, task dependencies, retries, alerts, Git-backed code, secrets, parameterization, environment isolation, idempotent outputs, backfills, observability, on-call ownership, and production runbooks. Question 14. A Databricks job fails with out-of-memory errors. What are the likely causes and fixes? Out-of-memory errors usually come from oversized partitions, expensive shuffles, cache data pressure, large collect operations, or Python serialization overhead. I first identify whether the driver or executors failed. Driver OOM often means collect, to pandas, or huge metadata. Executor OOM suggests partition sizing, spills, or skew. I would reduce partition size, avoid materializing huge objects, tune memory overhead, and rewrite transformations to stream data through iterators. Make sure to distinguish driver versus executor OOM. Then discuss collect, to pandas, skew, spills, partition sizing, cached data pressure, memory overhead, serialization, and iterator-based processing. Question 15. What is the medallion architecture, and why is it useful in a lakehouse? Medallion architecture is a layered lakehouse pattern. Bronze stores raw append-only data with minimal assumptions. Silver cleans, deduplicates, normalizes, and applies quality rules. Gold serves business-ready aggregates, dimensions, features, or dashboards. I like this pattern because it makes lineage and replay easier. If a rule changes, I can rebuild silver or gold from stable bronze. The risk is overlayering, so each layer should have a clear consumer. In your answer, describe the purpose of bronze, silver, and gold, raw retention, deduplication, quality rules, curated serving tables, lineage, replayability, and avoiding unnecessary layers. Question 16. How do you make Spark and Databricks pipelines testable and maintainable? I make transformations small, pure, and callable outside the notebook. Business logic lives in functions or packages, while notebooks mostly orchestrate. Unit tests use tiny data frames with expected outputs, including nulls, duplicates, and edge cases. Integration tests validate schemas, delta writes, and incremental behavior. I would also test idempotency by rerunning the same input. This matters at Databricks scale because data bugs are often more expensive than code bugs. Be sure to mention pure transformation functions. Packaging instead of notebook-only logic. Tiny data frame tests, edge cases, schema validation, delta integration tests, idempotency chips, and CI. Question 17. How would you design a scalable metadata service for millions of tables and files? I would separate the metadata API from storage and keep the hot path strongly indexed. The service needs table identifiers, schema versions, permissions, file manifests, and transaction history. I would shard by workspace or table namespace, cache frequently read metadata, and use optimistic concurrency for commits. Reads must be low latency, but writes must preserve correctness. For scale, I would add compaction of metadata, audit logs, and rate limits for noisy clients. While answering, focus on API design, table schemas, permissions, transaction history, sharding, caching, optimistic concurrency, metadata compaction, auditability, rate limiting, and separating metadata from storage. Question 18. What is the Catalyst Optimizer in Spark SQL, and how does it improve performance? Catalyst is Spark SQL's query optimizer. It parses SQL or data frame operations into logical plans, applies rule-based optimizations, uses statistics for cost-based choices, and generates physical plans. Examples include predicate pushdown, constant folding, projection pruning, and join reordering. I would not oversell it. Catalyst helps, but bad data layout or missing stats still hurt. In interviews, I connect explain plans to real performance fixes quickly. Make sure to cover logical and physical plans, rule-based and cost-based optimization, predicate pushdown, projection pruning, join reordering, statistics, code generation, and using explain plans. Question 19. What is the small files problem in Delta Lake, and how would you solve it? Small files hurt Spark because each file creates metadata overhead and scheduling work, even when the total data size is modest. They also slow Delta transaction log operations and Cloud Object Store listing. I would compact files with Optimize, tune output partitions, avoid over-partitioning by high cardinality columns, and use auto-compaction where appropriate. I would balance file size against parallelism, commonly targeting hundreds of megabytes for analytical workloads. In your answer, discuss why small files hurt scheduling and metadata, Delta log overhead, Cloud Object Store listing, compaction, output partition tuning, auto-optimize, and file size trade-offs. Question 20. Describe a situation where you would choose data correctness over latency in a Databricks platform. In a data platform, wrong fast results are worse than slow correct ones. For example, in financial reporting or feature generation, I would prioritize transactional writes, validation checks, and reproducible snapshots over shaving a few minutes. I would still optimize, but only after defining freshness requirements and error budgets. A good trade-off is serving approximate metrics for exploration while preserving exact delta-back tables for decisions, audits, and model training. Be sure to frame the trade-off using data correctness, latency, freshness SLAs, error budgets, transactional guarantees, validation checks, reproducible snapshots, approximate metrics, audits, and downstream impact. Question 21. How would you implement an LRU cache with O1 get and put operations? An LRU cache combines a hash map with a doubly linked list. The map gives O1 access from key to node. The list maintains recency, most recent near the head, least recent near the tail. On get, I move the node to the head. On put, I update or insert, then evict the tail if capacity is exceeded. The key is clean pointer handling and covering updates, misses, and capacity 1. While answering, cover the hash map plus doubly linked list design, O1 get and put, recency updates, eviction policy, edge cases, pointer safety, and capacity handling. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.